So notice how measurements work. You measure some quantity, let's call it Q. It could be momentum, energy, angular momentum, whatever. You measure some quantity Q. After you've measured that quantity Q, the wave function drastically changes from what it was before the measurement. Once you've measured the quantity Q, you will get some value. And the wave function must be such that it corresponds to quantity Q having that specific value. For example, we saw that with position measurement. Before the measurement, the wave function, I'm not showing the time dependence, just the spatial, it's kind of a cartoon, had some form. But after the measurement, you found, say this is 0 and this is L, you found some particular value, say 3/2 L, okay? And that means that the wave function after the measurement must respect the fact that the particle is definitely at 3/2 L, right? So this is 3/2 L. What wave function corresponds to knowing that the particle is definitely at 3/2 L? It's this, okay? And we saw similar with momentum. Once you've measured the momentum, you found the value, say, 3 pi over L times h bar. That means the wave function must be a wave function with a definite value of momentum of 3 pi h bar over L. What wave functions have different values of momentum? Plane waves. So the wave function has turned into a plane wave. Perhaps the concept of definite value is still kind of nebulous. To say that a wave function corresponds to a definite value of that quantity Q means that the expectation value, means that the standard deviation of that quantity Q in this wave function is 0, right? So definite value of quantity Q means, it means that Q squared, let me use a capital Q because that's what I've been, it means that the standard deviation of the quantity Q equals 0, i.e. Q squared minus Q quantity squared equals 0. Let's check on a couple of examples that the standard deviation of momentum is 0 in a plane wave state. And this will be good because it gives us extra practice with these things, expectation values, statistics, standard deviation, and so on. Okay, so let's check sigma of momentum equals 0 in a plane wave wave function. So I have a wave function that's e to the I k times x minus omega times t. It's not a normalizable wave function. So we discussed that on an infinite line, this cannot actually be a wave function of a particle. You have to combine a bunch of harmonics to build a wave packet, which is normalizable. But let's say if it's a particle in the box where x is restricted to be between 0 and L, then this is a legit wave function. Let's check that standard deviation of momentum equals 0. Okay, so first, expectation value of P equals between 0 and L psi star minus I h bar partial x of psi dx. Minus I h bar partial psi partial x equals minus I h bar over root L times I k times e to the I kx minus omega t. So expectation value of momentum is 0 to L to the minus I kx minus omega t minus I squared. So that's h bar k over, and then e to the I kx minus omega t over root L dx. Okay, so that's what we got. H bar k is a constant. So this becomes h bar k times integral between 0 and L, 1 over L times 1, because e to the minus I something times e to the I something equals 1 dx. This gives you h bar k, L over L, 1, it's h bar k. Okay, that confirms, well, that makes sense. If this is the wave function of wavelength of wave number k, it corresponds to a momentum h bar k. But how do we know that it's a definite momentum? In other words, as we keep, if we have an ensemble of such systems described by this wave function, and I keep measuring the momentum, how do I know that I always get h bar k? In other words, how do I know that the standard deviation will be 0? In other words, the distribution of results is infinitesimally thin. You don't get a spread of momentum. You always get h bar k. You never get 1.1 h bar k, 0.9 h bar k, 1.2 h bar k, but you always get h bar k. So that's why we want to check standard deviation. So the other ingredient we need is this. Okay, from 0 to L, e to the minus I kx minus omega t over root L. That's the wave function times minus I h bar partial x squared operating on e to the I kx minus omega t over root L. Let me use the square brackets. And sorry that I had to move this over to the other line. I know it makes some of you unhappy. Okay, I'm sorry. So minus I h bar partial x, this whole gadget squared is simply minus times minus, that's 1, I times I, that's minus 1, h bar times h bar, so that's minus h bar squared times the second derivative. So you can do the math and you will see that this is e to the minus I, all that stuff, over root L times minus h bar squared. And when you take two derivatives of e to the I kx, you're going to get ik squared, and then e to the I over root L dx. This gives you h bar k quantity squared. And so you get h bar k squared, 0 to L, e to the minus I, blah, 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 e to the I, blah, 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 over L dx. And again, you get h bar k quantity squared. Standard deviation of momentum is p squared minus p quantity, h squared equals square root of h bar k squared minus h bar k squared equals 0. This shows that a plane wave is a state of definite momentum. You will never get a spread of momentum values. If you have an ensemble of systems all described by a plane wave and you measure momentum, you will always get that particular momentum, h bar times the k of that plane wave. Similarly, if we have a state of definite energy like this, you can try to compute expectation value and I'm not going to do this. I don't have much time. But what you would do is, again, you would do a sandwich. You would do psi, sub n, h, operating star. And here I assumed that it's a discrete state. So I put the subscript n, meaning first level, second level. That's only true if it's a bound state, right? If the energy is less than the potential energy and all that business. N could also be on a continuous spectrum. So this is h, and then h squared would be, psi n star. You take the operator, you square the operator, dx. And if you grind through the math, you can use either method 1 or method 2. You will get these results right here. And in any case, you will see that when it's a wave function that corresponds to a state of definite energy, where the little psi's come from the solution of the time-independent Schrodinger's equation, right? With E being E sub n. Right, so this is right, and this is energy. It's the E that mentioned in the time-independent Schrodinger's equation. In any case, when you do that, you will find that, again, standard deviation is going to be basically it will be 0. If you have a state of definite position, what is a state? What's a wave function for a state of definite position? In physics, we call it a Dirac delta function. In electrical engineering, you call it impulse. It's an infinitesimally thin spike. And one can also, well, it's infinitesimally thin, so its standard deviation is 0. How to do this mathematically? There are ways to do it. I don't want to do that, but I think you're getting my point. That a wave function that corresponds to a definite value of some particular quantity is such that when you compute standard deviation of that quantity of a particle described by that particular wave function, you're going to get 0 standard deviation.